All right, let's dive deep into rock stresses and how they affect hydraulic fracturing. We're going to be looking at Chapter 4 of hydraulic fracturing today. So much to uncover here.
Yeah, they're invisible, but they're kind of running the whole show when it comes to fracturing. They decide how fractures form, where they go, how much we can even get out.
It's like we're getting X-ray vision into the Earth. We can kind of predict how those fractures are going to behave, which is super important, right?
Yeah, definitely. And the chapter starts off throwing all these pressure terms around. Reservoir pressure, fracture closure pressure, bottom hole treating pressure. I mean, it's a lot.
Yeah, I felt that way too. But figure 4.1 helps. It's like a pressure map for the whole process. But before we even get into all that, I have to ask about something. It blew my mind when I learned it. Everyone thought for years that hydraulic fractures were always horizontal. Makes sense at first, right?
Yeah, you'd think so. But then back in 1957, that whole idea got flipped around. Hubbard and Willis, they were geologists. They looked at how normal faults work, the type where one block of rock slides down. Well, they realized that for that to even happen, the horizontal stress has to be less than the vertical. It changed everything.
So they were seeing evidence of vertical fractures happening naturally, just on their own.
Yeah, exactly. And their work just totally changed how we understand how these forces work together. And that takes us to the two main types of stress we're dealing with here, vertical and horizontal. Vertical stress is pretty straightforward. It's just the weight of all the rock above pressing down.
Right, like we're the filling in a giant rock sandwich.
And figure 4.2 shows that it averages out to about 1.05 psi for each foot you go deeper. It's like a pressure gauge built right into the Earth's crust.
So deeper you go, higher the vertical stress. Makes sense. But then there's horizontal stress, which I'm guessing is more complex.
Yeah, it is. It's like a tug of war. Some of it comes from that vertical weight we talked about, but the other part's from tectonic forces, those big movements of the Earth's plates. And to know how much each one contributes, we've got to look at things like how stretchy the rock is.
Hold on, stretchy. Like a rubber band.
Yeah, exactly. Rocks have some give to them, and to measure that, we use this thing called Poisson's ratio. So imagine squeezing a block of rock, from the top. It compacts vertically, but it also bulges out sideways, right?
Okay, I can see that. So the more it bulges, the higher that horizontal stress is?
You got it. A higher Poisson's ratio basically means the rock pushes outwards more when you squeeze it, and that outward push, that's horizontal stress.
That's really cool. So we can actually calculate horizontal stress based on the vertical stress and how much the rock bulges.
Exactly. And for most rocks, that ratio is around 0.25. That means the horizontal stress is about 1/3 of the vertical stress. And what's really amazing is that this calculation, the theoretical one, actually matches up pretty well with what Hubbard and Willis saw in those natural faults.
So our theory matches reality. Well, at least sometimes, right?
Of course, there's always more to it. Remember those pressure terms we were talking about? Reservoir pressure, the pressure from the fluids inside the rock plays a huge role too.
Because it's pushing back against the weight of the overburden.
Exactly. Imagine a balloon, filled with air. It's harder to squeeze than an empty one, right? The air inside is pushing back. Same thing happens in rocks. We have to account for that internal pressure to understand how much force is actually squeezing the formation.
So it's not just the weight of the rock above, but the net effect of that weight minus the pressure from the fluids inside. And that's what they call effective stress in the chapter.
Exactly. You got it. It's like adjusting our pressure gauge to account for the internal pressure. And when we do that, our calculations get way closer to what we actually see happening in the field.
Okay, so we have vertical stress, horizontal stress, and effective stress. Anything else trying to blow our minds here?
Oh, of course. Don't forget about those tectonic forces we talked about before. All the different geological structures, like faults and folds, make unique stress situations that can really affect how fractures behave.
Okay, let's get into those. We talked about normal faults,
Yeah.
where horizontal stress is lower. What about the other types?
Well, reverse faults. They can be a real pain when it comes to hydraulic fracturing. Imagine trying to make a nice vertical fracture, but the rock's already squeezed so tight horizontally that your fracture goes sideways. It's not only inefficient, it can be dangerous too.
And then there's those strike slip faults, where the stress is so high that they make new fractures just while you're drilling.
Yeah, those are called drilling-induced fractures. They can create really twisty paths for fluids to flow through, and that makes it hard to get the fracturing fluids right where we need them.
Wow, so not all faults are the same when you're doing hydraulic fracturing. What about anticlines? They have that arch shape, right?
Yeah, and because of that, they can have really low closure stress, the force that holds the rock together. It can be hard to even make a fracture there in the first place.
So it's like a balancing act. Too much stress, you get unwanted fractures. Too little stress, you can't even make a fracture.
Exactly. And to add even more to it, let's talk about salt.
Salt. What does salt have to do with any of this?
Well, it turns out salt acts like a fluid under geological pressure. It makes these high pressure zones that actually pull hydraulic fractures towards them. Imagine trying to make a nice controlled fracture and suddenly it goes off course because it's attracted to a big chunk of salt.
No way, that's wild. So all these different forces are pushing and pulling on the rock. And to know where those fractures are going to go, we have to understand how these forces all work together.
Exactly. And it's not just how strong they are, but the direction they're pushing too. It's the difference between the minimum and maximum horizontal stresses that determines where a fracture goes and its azimuth.
Okay, that makes sense. But can you explain that a bit more? How do those stress differences decide where the fracture ends up?
Well, think about a layer of shale over a sandstone reservoir. Shale's less permeable, so it usually has a higher minimum stress than sandstone. That stress difference acts like a wall, stopping the fracture from growing up into the shale.
So the bigger that difference in stress, the better it keeps the fracture inside the sandstone.
Exactly. And that's why it's so important to understand these stress differences. If we want to keep the fracture in a specific zone, we've got to know where those natural barriers are.
This is all really fascinating. But my brain's feeling a little full with all this stress and pressure. I think we need a break to let it all sink in.
Yeah, good idea. Let's come back after a short pause. Welcome back. Ready to keep going with these rock stresses.
Yeah, for sure. It's crazy how much is going on under the ground that we don't even think about.
Right. And as we dig deeper into this chapter, you really see how important these invisible forces are to make hydraulic fracturing actually work.
Yeah, it's not just about like pumping stuff down there and hoping for the best. We're actually trying to like design these fractures to get the most we can out of a reservoir.
Exactly. And that all goes back to predicting and controlling where those fractures go, how big they get and how well they stay open.
Okay, so let's talk about that. How do we use what we know about these stresses to make better fracture treatments? I know we said minimum horizontal stress is important because it tells us how much pressure we need to even make a fracture to begin with. But what else do we need to think about?
Well, those stress barriers we talked about, the ones from different types of rock, like that shale over sandstone thing, that stress difference is kind of like a lid keeping the fracture in the sandstone.
Right, right. We need to know how much that fracture might want to grow upwards.
Exactly. And the chapter says there's like a rule of thumb that the biggest stress difference between the shale and sand is usually less than zero point 0.2 psi for each foot you go deeper. But that's just a general idea, right?
Because things like reservoir pressure going down can change that.
Yeah, exactly. When the pressure inside drops, the effective stress in the sandstone goes down too, and that can make that stress difference even bigger.
So we always need good pressure data to make the right decisions. Okay, so stress differences help us figure out how high the fracture might go. But what about when things get messy, like when we get those secondary fractures that make really complicated shapes?
Ah, yeah. Those T fractures, the ones that branch out and turn. It doesn't always look like a perfect vertical crack, like in the textbook.
And that's probably not a good thing, right? Does that mean the fracture treatment isn't working as well?
Well, sometimes, yeah, but not always. Sometimes those T fractures can actually help. They create more surface area, so more oil and gas can flow in.
Okay, so not always bad, but it can cause problems, like a screen out, right?
Yeah, that's when all that proppant, the tiny grains that hold the fractures open, gets stuck near the wellbore. It's like clogging a pipe. Happens when the fracture's too complicated or the pressure's too high.
And then there's those natural fractures. They can make things unpredictable too, right? What happens when a hydraulic fracture hits one of those?
Well, it depends. Sometimes it just crosses over, no problem. But if the pressure's too high in the hydraulic fracture, it can open up that natural fracture, and that's a way for fluids to escape.
Oh, so it's like a leak in our nice plumbing system.
Exactly. And that can really affect how well the whole treatment works. Which brings us back to why it's so important to measure the in-situ stresses as accurately as we can.
Right. The better we understand all those stresses, the better we can predict and control how those fractures are going to act. And we've got those 3 ways to measure them: injection tests, shear wave sonic logs, and measuring the strain on core samples.
Yeah, and injection tests are the best, the gold standard, because they actually measure how much pressure it takes to break down the rock and make a fracture. It's like a tiny version of a hydraulic fracturing treatment.
But I remember you saying they could be expensive and take a lot of time.
They can, yeah. That's why we often use shear wave sonic logs. They're more practical. They measure how fast sound waves go through the rock. The faster the waves, the stiffer the rock, and the higher the stress.
So it's like using sound to make a map of the stress under the ground.
Exactly. And they're not as perfect as the injection tests, but they can still give us good information when we use them with the direct stress measurements.
Okay, so we can use a bunch of different ways to get a good picture of what's happening down there.
Right. And once we have that, then we can start thinking about things like proppant stress, the force that's pushing on those tiny grains of proppant that keep the fracture open.
Right, because if those get crushed, the fracture closes back up and we're back where we started.
Exactly. And proppant stress is affected by a lot of things. The closure stress that's trying to close up the fracture, how wide that proppant pack is, and even the pressure of the fluids going through the fracture. And there's actually an equation for it, equation 4.19.
Wow, there's a lot of math in all this.
There is,
Yeah.
but the main thing to remember is that we want to keep that proppant stress as low as possible so those fractures can flow and we get as much oil and gas as we can.
Okay, so we've talked about all kinds of stresses, stress barriers, how complicated fractures can get, how to measure them. That's a lot of information. But before we finish, there's one more thing I want to touch on. Wellbore breakdown. What is that and why should we care about it?
Wellbore breakdown is when the pressure inside the wellbore, the hole we drilled, gets so high that it breaks the rock around it.
So it's like the wellbore is fracturing.
Exactly. And those minimum and maximum horizontal stresses we've been talking about, they play a huge role in whether that happens or not.
We're back for the last part of our deep dive, all about rock stresses and hydraulic fracturing. I feel like I've learned a whole geology course just now.
It's a lot to take in for sure, but hopefully we've made it all a bit clearer. So in this last section, we'll try to tie everything together, see how all this works in the real world.
Okay, so we've talked about how to measure in situ stresses, but then how do we actually use all that to make better fracture treatments? There's just so much to consider.
Well, knowing that minimum horizontal stress is like the first step, that tells us how much pressure we need to even make a fracture. But there's way more to it. We need to also think about those stress barriers, right? From the different types of rock, like that shale and sandstone example we keep talking
Right,
about.
because we want to keep that fracture where it belongs,
Right.
in the target zone.
Yeah, exactly. So if we're trying to keep it in the sandstone, we need to know how much higher the stress is in that shale around it. That's going to tell us how much that fracture might want to grow upwards. And remember, those stress differences can change depending on things like the reservoir pressure.
Right, so it's not like a set number you can just plug in. It's more like all these things working together.
Yeah, it's like a big puzzle. We're trying to figure out how all the pieces fit.
Speaking of puzzles, how do you deal with those secondary fractures that form, those ones that make all those weird shapes? Is there any way to, make those less likely to happen?
The main thing is managing the pressure inside that fracture. If we can keep it lower than what it takes to make new fractures, then we have a better chance of keeping the fracture how we want it, more predictable.
So enough pressure to make that main fracture, but not too much that it goes crazy, branches out everywhere.
Yeah, exactly. That's where the science and the art of hydraulic fracturing come together. We have to design the treatment just right, change things like the pumping rates, what kind of fluid we use, how much proppant. It's all about finding that right balance.
And then we have to watch everything super carefully, right? Make sure it's all going to plan.
Oh, yeah, for sure. That lets us change things up if we see something's not right.
Okay, so managing that pressure is super important. And then there's the proppant stress. The force on all those little grains of proppant, the ones keeping the fracture open, we definitely don't want those getting crushed.
No, definitely not. If they get crushed, the whole fracture can close up, and then it was all for nothing. And proppant stress comes from a lot of things. The closure stress pushing to close the fracture, how wide the proppant pack is, even the pressure from the fluids moving through.
So that's just another thing we have to think about.
It is. But remember, the more we know about all these forces and how they connect, the better we can get at making good decisions, to get the most out of our fracture treatments.
Okay, so let's zoom out a little bit. We've talked about all these different rock stresses, where they come from, how they affect fracturing. But what does it all mean for, like, oil and gas production in the future?
That's a great question. As we keep pushing to get more unconventional resources, understanding rock stresses is going to be even more important. The reservoirs are getting more complicated, the wells are deeper, and there's less room for mistakes.
So we have to keep getting better, smarter about how we do things.
Exactly. And there's so much cool research going on, new ways to measure, better computer models, even ways to maybe change the in-situ stresses to work for us.
Wow, that's amazing. It sounds like there's a lot of potential in this field.
Oh, definitely. The more we learn about these forces underground, the better we can use them to get all that energy out of these tricky formations.
Well, I feel like I know so much more about rock stresses and hydraulic fracturing now. It's amazing how much goes into something that we can't even see.
It is, and this deep dive has shown just how important it is to understand those invisible forces if we want to do this right.